this video we will calculate EMF. EMF stands for electromotive force. It's just a fancy vocabulary term for voltage. Of a cell, remember a cell must consist of an anode and a cathode. The anode loses electrons, the cathode gets reduced and gains those electrons. So what is the EMF of a cell of a Pb plus 2 going to Pb half cell with an H plus going to H2 half cell at these concentrations and pressures? The PT stands for platinum, so you don't really need to worry about that because the H plus is in water and H2 is a gas, so platinum is the surface upon which the gas is collected. But the platinum there means nothing in terms of solving this problem. We're at non-standard state conditions, which means we have to use the Nerst equation, and we got to figure out the voltage of this non-standard state cell. So first is we have to write our Nerst equation out. So let's go ahead and write our Nerst equation. The Nerst equation is E under some non-standard state conditions equals E cell minus 0.0257 divided by n natural log of Q. So let's look at our two cells here, half cells, and see which one is going to get oxidized and which one is going to get reduced. Right, so we have Pb plus 2 going to Pb solid. Right, in order to balance this, this Pb plus 2 has to gain 2 electrons. So that's a reduction. So 2 electrons plus Pb plus 2. Okay, here we are right here, and that is minus 0.13 volts. Okay, we'll keep it as is. And then what's the next part of our half cell? The next part of our half cell is H plus going to H2 gas. So H plus going to H2 gas. Okay, if we want, we can put our states in just to be very thorough. So H plus going to H2 gas, I believe, if I'm not mistaken, that's going to be 0. Yeah, it's 0. You see this here? Okay, H plus going to H2 gas, that's a 2 electron gain, and that's 0. So here we gain 2 electrons. Once out the hydrogens also. That's 0.00 volts. Okay, once again, you see that in our table here. Okay. Well, both of these are reduction reactions. Both of these gained 2 electrons. That's not how a battery works. One of these will have to get flipped, and if this were to be a successful battery, we need a positive sign for our E cell, which is the cathode and the anode together. Let's flip this first reaction. Okay. So we'll flip this reaction. So flipping this reaction, we will get here lead solid, and that's going to go to lead plus 2, aqueous plus 2 electrons. And flipping that will actually flip this sign to positive 0.13 volts, and that's going to give us a positive E cell. So our 2 electrons will cancel out. Can never have free electrons floating around in our final answer. So our final answer is lead solid plus 2H plus, and that's going to go to lead, adding these two equations together after we flip this first equation, and this is going to be positive 0.13 volts. This gains 2 electrons, so that's the cathode where reduction happens. We flip this reaction, we flip it, it now lost 2 electrons, and losing 2 electrons is where oxidation happens, also known as the anode. So this is E cell, but what we want is E at very specific concentrations. So we figure out Q, we compare it to K, so it has the same equation as K. And it's going to be the concentration of lead plus 2 times the pressure of H2 gas divided by the concentration of H plus, and we have to square it. Okay, we have to square it because there's 2 hydrogen ions there. All right? That Q is going to go here where we take the natural log. So remember, Q is the same equation as K, but it tells us which way the reaction will shift, either to the reactant side or the product side. It tells us which way the reaction will shift based upon, in comparison to the equilibrium constant K. All right, so what is our concentrations here for this non-standard state problem? Lead plus 2 is 0.10 mole. Lead plus 2 is 0.10 mole. Pressure of hydrogen gas, H2 gas, is 1 atmosphere. I'm not putting units because Q and K are unitless. And H plus, proton, is 0.050, but we have to square it. Okay, don't forget to square it. So let's solve for Q here in our calculator. 0.10 times 1 is just 0.10, divided by 0.050 squared, and that's 40. Okay, so that's my value of Q. It's 40, and that's going to go right here into our Nerst equation. Okay, so let's plug everything here into our Nerst equation. Times natural log of Q, we already figured out that Q is equal to 40 here. All right, so that's going to equal to A, or excuse me, that's going to equal to E. So we can do this in one fell swoop. Natural log of 40 times 0.0257 divided by 2, and take the minus of that, and that's plus 0.13, and getting 0.083 volts. And that will be our answer for E. Not E cell, but standard state. Standard state would mean everything would be 1 molar and you'd be at 25 degrees. This is the voltage that we get for this battery under these concentrations, which are non-standard state.